Hello students, welcome to a class of Topology. In this video, we are going to discuss about second countable space. Okay, we begin with definition. A topological space, X2 is called a second countable. X2 is called a second countable, or it's said to satisfy second countability axiom, or it is said to satisfy axiom of second countability or second axiom of countability, second axiom of countability if it has a countable base. Countability if it has a countable base. That is, when a topological space has a countable base, we say that the space is second countable. Okay, we will see some example. Our usual space realigned with the usual topology 2U. 2U is represented as usual topology, standard topology. Okay, this space is a second countable space. To prove it, we need a countable base for it. Okay, already we know that script to be equal to collection of all open interval AB where A comma B varying over real number A less than B is a base. It's a base for this topology. Now I consider another collection B dash which is equal to collection of open interval AB such that A comma B varying over Q rationals A less than B, where A and B are real number varying over any real number, script B is a base. By same steps of proof, we can prove that B dash is also a base for this topology. Moreover, B dash has an extra property that were the left and right points of the interval varying over rationals. So B dash can be one-to-one correspondence with the Q cross Q. Okay, so that collection B dash is, since Q cross Q is countable, collection B dash is countable. Therefore, script B dash is a base for the usual topology of real line, also it is countable. Therefore, real line with the usual topology has a countable base which is B dash. Therefore, usual topology, real line with the usual topology is a second countable space. Okay, it is countable. Therefore, real line with the usual topology is second countable. Another example of a second countable space is every metric space. Every metric space is second countable. For that, let XD be a metric space. M must denote metric space, okay? Metric space. And we already know that script to be equal to collection of BD open balls centered at X with radius R, where R is varying over real number. Form a base for this topology. A comma X is an element in capital X. Okay, we know that this collection is a base for metric space. Then I would like to change on this radius. Let collection B dash is equal to, again, open ball centered at X with radius R, but the radius varying over rationals x varying over x. Then this collection can be equivalent with the countable set Q. Since Q is countable, B dash is a script B dash is a countable base for the metric topology of X. Therefore, every metric space is also a second countable. Now we are going to answer some questions based on this base for a topology. Okay. First question is, does a topology always have a base? Does a topology on a set always have a base? Yes. Yes, because every topology can be considered as a base for a topology. Therefore, every topology will always have a base. The topology itself can be considered as base of it. Therefore, every topology always has a base. Okay. So next question is, can a topology on a set have distinct bases? Of course, a topology can have different bases, distinct bases. Different bases on a set X. For example, if you consider real and with the usual topology, then as in the previous example, B equal to collection of all interval of the form a comma b varying over real number is a base, and B dash is equal to collection of all open interval a b with a and b are varying over Q is also a base. So of course a topology can have more than one basis. Next question is, if Tau1 and Tau2 are two topologies on X, V2 topologies on a set X. So, with the property that Tau1 and Tau2 have same base, such that Tau1 and Tau2 have same base. Then what will happen to these two topologies Tau1 and Tau2? We can prove that then is Tau1 and Tau2 same? Are Tau1 and Tau2 same? Yes. If two topologies on a same set have same base, then that topology will coincide. That means there exists only one topology with one base, common base. We will prove this result. Let Tau1 and Tau2 be two topologies on X such that Tau1 and Tau2 have same base, common base, script B. We are going to prove that Tau1 and Tau2 are equal. To prove Tau1 and Tau2 are equal, to prove Tau1 equal to Tau2, we have to prove that Tau1 is stronger than Tau2 and Tau2 is stronger than Tau1. Okay, Tau1 contained in Tau2 and Tau2 contained in Tau1. Okay, now let U be an open set in the topological space X Tau1. That means U is a member in Tau1. Okay, then since script B is a base for Tau1, U can be written, this open set U can be written union of base elements by the definition of base. When the set U can be written as union of elements from B, which also implies U is a member in TOT2, because script B is also base for TOT2. So when you consider U in TOT1, U automatically belongs to TOT2, which implies TOT1 is contained in TOT2. By the reverse argument, we can prove that TOT2 is contained in TOT1. Therefore, TOT1 and TOT2 are equivalent or same topology on X. When two topology have same base, they will be same. Now, another example. Consider X, the discrete space X with a discrete topology, power set topology. We already know that script B equal to collection of all singletons X varying over capital X form a base for tau. It's a base for TOD, discrete topology TOD. For TOD denote the discrete topology, discrete space. X with a discrete topology is called a discrete space. Okay. Then, is it a second countable space? If it is second countable, its base it should have a countable base. The only base of discrete topology is collection of singletons. So, X TOD is second countable only when this base is countable. What will happen if script B is countable? Script B is actually varying with respect to varying elements in capital X. So, we can see that the countability of script B is based on countability of X, right? Cardinality of X. Therefore, B is countable only if X is countable. Right? So, the discrete space has a countable base only if X is countable. That is, discrete space has a countable base only if X itself is countable. Therefore, we can say that a second discrete space is second countable only if X is countable. Therefore, we can note that a discrete space is second countable only if and only if and only if X itself is countable. Another example of a second countable space is real line with the semi-open interval topology denoted by tau LS or tau RS. What is tau LS? Collection of all A subsets of real line such that for every A in R, there exists R greater than 0 such that left closed A, A plus R is contained in A itself. This is the lower limit topology or semi-open interval topology of the form closed interval A, A plus R. Okay. And you can prove that this is a second countable space. We already proved that script B is equal to collection of all A, B, where A, B varying over real number. A less than B is a base for this topology. We know that it is a base for this topology. Base for tau LS. Then if you change these elements from A and B from Q, this collection will be countable. So which is equal to collection of all A, B such that A and B are varying over rational numbers. A is less than B is also a base. Then B dash is also a base for tau LS. and an extra condition that when A and B are varying over Q, this collection will be equivalent to Q cross Q. Since Q cross Q is countable, collection B dash is countable. Since Q is countable, B dash is countable. So this topology has a countable base, therefore it is a second countable space.